Okay, we're going to continue our talk about operations on two-dimensional vectors. And in this video, we're going to look at addition and subtraction of 2D vectors. So addition and subtraction. Addition and subtraction of two-dimensional vectors. All right? And so we'll start this first example. We'll look at it visually, and then we'll look at how to add vectors without drawing pictures. But it's certainly good to conceptualize what's happening when you add them. So let's consider the vector 2, 4 plus the vector 7, 3. So we'll keep everything positive for this first example. And we may not need to do another example. We'll see how it goes. So we'll start with our first vector, 2, 4, which means right 2 and up 4. So I'll pick a starting point for this vector. Maybe it's down here. And I'll go right 2, so I'll call that 2. And then I'll go up 4. And maybe it looks something like this. Starts here, terminates there. And so the vector 2, 4 looks something like that. Okay? So that's the vector 2, 4. Now, when you're adding vectors, visually what's happening is you look at something called the tip and the tail of the vector. So when you look at a vector, the tip of the vector is where it terminates. It's where the arrow is. So this is the tip of the 2, 4 vector, and this is the tail. Like if it were traveling, this would be the first point that hits every spot in space. So this is the tip, and this is the tail. When you add vectors, what you do visually, so when you add vectors, you connect tip to tail. Connect tip to tail. So what that means is where the 2, 4 vector terminates, where the tip of it is going to be where the 7, 3 vector starts, where its tail is going to be. So right here is going to be the initial point of my 7, 3 vector, or the tail of my 7, 3 vector. So from this point, I'm going to travel right 7 units. I'll make that approximate, and I'll travel up 3 units. Maybe it looks like that. And so the 7, 3 vector looks like something like this. Okay? So this is what you get. This is the diagram you get when you look at stacking the vectors tip to tail, because we're adding them. But what is the answer to 2, 4 plus 7, 3? Well, it's this new vector that we get. The new vector that we get circumvents everything happening in the middle and says, okay, where did this system of vectors start originally? Well, the original system of vectors started right there, and the whole system terminated. If you travel this path, it terminates here. So the new vector we get, I'm going to try to draw this as straight as I can, something like that. That vector is the answer to this sum, this addition of vectors. So what is this new vector? And you're going to see why drawing the pictures for this can be kind of confusing, can be kind of tough, unless you're very systematic. Okay? So if I'm looking at this black vector, I want to know the components of it. So its horizontal component is this, while its vertical component is this. So in other words, how far do you have to travel right for this vector? Well, if you're looking at it, it should be pretty easy, because the first vector required to travel of 2 units to the right, while the second had an additional 7 units to the right. So this distance here is 2 plus 7, and then of course that's 9, right? So this black vector, the horizontal component of the black vector, simply takes the horizontal component of the first vector and adds it to the horizontal component of the second vector. So when you add these vectors, 2, 4 plus 7, 3, this black vector that I have here has a horizontal component of 2 plus 7, comma. The vertical component, I'm sure you're guessing, probably way ahead of me here, is going to be, well, how far up, how much vertical distance do you travel? Well, you've got a vertical travel of 4, plus another vertical travel of 3. So this distance here is 4 plus 3, which of course is 7. So here we added the horizontal components to get the new horizontal component. And just like you would guess, we also add the vertical components to get the new vertical component. So this new vector that we get is the vector 9, 7. Okay? Now, the good news is, if these are positive or negative, it doesn't matter. You still do the same thing. So let's do another quick example without a diagram, looking at anything tip to tail. So let's consider let's determine, and you'll see how easy this is, determine negative 3, 9 plus 17, negative 12. Well, it's pretty simple, right? You add the components together. So you're going to get negative 3 plus 17 results in a total horizontal component of positive 14, while 9 plus negative 12 results in a total vertical component of negative 3. And that's all there is to it. Now, there's an advantage sometimes to writing your vectors using your ij notation. So let's look at another one. Let's determine, let's do negative 3, 9 minus 17, negative 12. Now you may wonder how to do this because it's subtraction. You can easily change it to addition. We can talk about that in a moment. But you'll probably be able to figure this out anyway. But let's look at it in terms of I and j. This is the same thing as the vector negative 3i plus 9j, right? Negative 3i plus 9j minus the vector 17i minus 12j. And now in this notation, there's no commas or any angle brackets or anything weird like that. It just looks like algebra. So if you were doing algebra here, you would distribute the negative. And so you would get negative 3i plus 9j. We'll drop these parentheses. Minus 17i plus 12j. And then we combine like terms. So I've got negative 3i minus 17i is negative 20i. Guys, all that means is we're adding the horizontal components because the I hats are the horizontal components. Plus, add the vertical components or the j hat terms and get 21 j hat. So you can write it like that, or if you go back to your angle brackets, it's negative 20, 21. All right? Now, you don't have to convert to ij notation. What you do is you simply, if you do it without converting, it's pretty straightforward. You could do it like this. Let's not use purple. You would take negative 3, 9. Sorry. You would take negative 3 minus 17, which is negative 20, and you would take 9 minus negative 12, which is 9 plus 12, which is 21. Okay? So you just subtract the components, negative 3 minus 17, and 9 minus negative 12 instead of add, and you get the same exact answer. All right? So that is addition and subtraction of two-dimensional vectors.